today's tutorial is about really entering the point of transporting. So we saw the ideas from quantum couplings, right? And also yesterday's talks by Augusto, they were very focused on the idea of finding a coupling, so a joint state with given marginals. And this is where we left also our first tutorial. Today, instead, we're moving towards the idea of transport plans. Okay, so really, can we move mass, so not mass, say, can we move these quantum states? How can we move? What should we use? And this will bring us first to general considerations about transport plans and couplings and a specific construction that maybe you haven't seen, which is the purification of a state, which is very quantum as a construction. And then we establish a correspondence between couplings and plans. But we're going to see that these couplings are slightly different than the one we saw yesterday from the Gauss-Mucho-Paul-Cagliotti approach. Then we're going to try to build a quantum optimal transport from this notion of channels. We see I'll fix a cost, so one can build a general theory. There's been some attempts going beyond the quadratic cost, but then I stick with the quadratic cost because I think it's very rich already as a case. And because we have a lot of mathematical open questions here. And later on, maybe I try to mention some things about the Gaussian case, but this forces us to go to infinite dimensions, so I will really be quick on this. Okay, so let's start from the classical optimal transport. So we want really to transport mass, remember probability, say now in this case now it's rho into sigma, but maybe also the reverse, okay? Rho into another probability sigma. And we said that Kantorovich found the idea of building couplings, right? So joint probability distributions and then you look at the marginals. But if you think in terms of probabilities, you don't have a map if you have a coupling, right? You would like to say, okay, but if I have point X, I'd like to know what is the probability that I move this point to point Y, right? So what you should actually relax the problem is not in terms of couplings, but in terms of these plans, which are Markov kernels. These are the same that appears in Trifon's lectures yesterday, okay? So you see, there's a slight difference, but which say it's trivial, just dividing by rho. Of course, you say, well, this should be defined on the support of rho, so where I can actually divide, right, in some sense. Otherwise, if I really don't have mass at X, I don't care where I move it, okay? But this gives you a notion, still relaxed notion of transport map, but more related about a rule to move points from one place to another, okay? So this is a Markov transition kernel. What do I mean? As the lecture, yesterday's lecture, so for every X, if you look at this as a probability with respect to Y, so as a function of Y is a probability, okay? And then it's also measurable with respect to X, but we forget about measurability here, okay? So the point is now to propose a quantum optimal transport where the plan is the key object, okay? This sort of transport map. And this plan will be a quantum channel. Okay, so you can start now from this point of view and try to build a theory. Maybe you end up in the same theory as yesterday, like the Gauss-Mucho-Paul-Cagliotti. Well, actually, you end up with something very similar but different. Okay, so it has different properties. There are some properties we cannot prove in the case of the Gauss-Paul-Cagliotti approach. Okay, so let's be then very clear with the definition. So what is for us sorry, I can read from here. Right. Okay, recall that a quantum channel we defined yesterday is a completely positive, there was this condition, trace-preserving linear map, acting on operators and preserves states in particular. Now, if we define, given two quantum states, sigma and rho, let's say now that rho is our source, okay, we want to find a quantum transport plan with write phi, which will be a plan, let's call it M from rho to sigma, is a quantum channel such that phi of rho equals sigma. Okay, as simple as that. But now we have a notion of plans. Okay, now the point is how can we compute a transport cost along the plan? This is now the problem. We have a good notion of plan, but it's not really as simple as writing trace of C phi, right? Because phi is now an operator which maps operators on H into new operators on H. So it's more complicated than that. So what we need to build a system, and possibly a joint system, where two copies of rho exist somehow, or matter a copy of rho and a copy of sigma, which are same but strongly correlated. Okay, this is the idea. Of course, you can say, well, take the rho tensor product phi of rho, but this will be sigma, so this is just maybe one possible choice, but we want to make these copies very correlated. And so the strategy will be this. We take, so in some sense, we make a copy of rho, and then we act with phi on one of this copy, and we leave the other fixed. So in this way, we can sort of build these two correlated copy of rho and sigma. Okay, this joint state. So what is the technical tool that we use? Well, first of all, let me recall a couple of generalities here. So remember that we have a Hilbert space H, which is our quantum system, and we have its dual. Now let's write H star as the dual. And remember that we have an identification between a space and its dual, okay, simply given by the Riesz map, but in this case, it's just a matter, if you want, of notation, because we use ket vectors for H and bra vectors for H star, okay? Now, if you have now an operator from H to H, you can define its adjoint. Now, the definition is this one. So the adjoint is still an operator from H to H, which maps a state phi or general vector, ket vector phi into this new ket vector A dagger phi. What is the property of the adjoint? It's adjoint with respect to the scalar product. Okay, so whenever you apply A to phi, you take the scalar product. Sorry, you should take any general psi here, not only for phi. Okay, in particular, this holds for phi, but you should require for any pairs phi and psi. Okay, and then you can push, take the scalar product. Sorry, you can apply the adjoint to the other vector, right? Okay, I hope you know the adjoint. Okay, this is just a partial, so it's a misprint. You should take two general vectors, phi and psi. Then you can also do another thing, which is the so-called transpose operator. In this case, you sort of just transpose and not take the conjugation, because the adjoint, if you think in terms of matrices, would be the transpose conjugated. So how can you formally define this? Well, you have the dual Hilbert spaces. So the transpose goes from the dual to the dual. So it takes a bra vector and gives you another bra vector. Let's write it A transpose phi, bra phi. And the condition that we require is essentially this, that this is a linear operator. How it acts? Well, it acts on H by first applying A and then taking scalar product with the phi. Okay, this is a well-defined element in the dual. Now, if you're already lost, let's think in terms of coordinates. So if you pick an orthonormal basis with H, you will have a corresponding dual basis. Let's simply denote it with bra I, where just a notation. Okay, you take a basis and the natural dual basis. So what happens? That the adjoint is really the transpose conjugated matrix of the original matrix, which represents A, and the transpose is simply the transpose. Okay, just as simple as that. But these definitions show that it does not depend on the choice of the basis. Okay. And now we're finally for the key construction, which is very interesting, and I think it explains. So it shows that something in the quantum case can be done, but classically cannot be done. Okay. So this is the so-called purification of a state. So given a state rho, what is the purification? So the purification, I think, is a concept that goes back to Schrödinger, I think. It's a very old idea. And so if you have a state, remember that this is a state operator, okay? So state operator or a density matrix, okay, not really already a vector. So it may in general not be pure state. It does not correspond to a single vector, state vector or wave function. So the idea is, well, maybe we can purify this rho by imagining that there is a larger system. So in this case, a larger system is a tensor product of H tensor some ambient space K, another system K. And in this larger system, maybe we have a pure state. So I write it as a state vector, so that if you do the partial trace, so if you look at the marginal back on H, so you trace out K, well, you end up with rho. Okay, so this rho that we see as something which is not pure, is so-called mixed, is actually, say, the marginal of a pure state on the universe. If you think maybe this K, you are adding everything else. Okay, So what is an example? Because this is a phenomenon that classically cannot be read. Because if you have a pure state, if you think in terms of random variables, means that you have a Dirac law, so it is a constant random variable. And if you look at subsystems, so if you look at marginals, they will be constant anyway. Instead, this is something that in quantum probability instead exists and is very useful. And the key example is already the old Bell state, right? Because remember, the Bell state, now I'm writing in just in a system of 2 qubits. The Bell state is pure. There is a state vector here. So if you think of the projection on this state is a pure state. But now remember there was this exercise that if you look at the marginals, so if you do the partial trace, say you trace out the second, you will get a mixed state. Actually, you have this state here, which is just the 1/2 the identity. Okay, so this is a key example that shows that sometimes maybe this can be done to find a pure state on a larger system, which is so-called purification of a given state. So now the point is that we are not starting from a pure state and we trace out, but we are given rho, and we want to find, say, the analog of a Bell state. But actually, the Bell state structure is very, you see, you have 1/2 here and 1 over square root of 2, because now you need to take this and pair it with its bra. And again, you see, there is some similarity. If you do the math, actually, in this example, I don't know, I gave you as an exercise, so maybe I hope you did it yesterday. No, but now we are going to do the general construction. You see, there's really a similarity. So it's really based on the idea of the Bell state. I mean, all this computation, I find it very natural if you think in terms of the. Now, there is also some warning here. So the space, so the purification is not unique in some sense. There are plenty of them. Because if you start with a pure state and you act, for example, with the identity tensor a unitary, which is only unitary on K, so if you keep it pure but evolving only the universe, well, if you do the partial trace, it doesn't matter. So the partial trace, you trace out K, you will anyway find the rho, okay? So you can always, for example, do this, but also you can enlarge the system by adding something extra, and this will not be seen in the partial trace, okay? So remember, there is no unique purification, but there is a so-called canonical purification, and which is based, and this is where we essentially restrict ourselves. If you want, it's like saying there are plenty of probability spaces where a pair of random variables with given laws exist, but in optimal transport, you reduce yourself with the product space. So in a sort of, you select one, which is useful. So you don't need to, for example, maximize or minimize over the set of all possible probability spaces, but only on this canonical setting. So the canonical setting for the purification is to say this. First, you need to do this identification. Sorry, now I'm a bit too technical, but the point is, if you have the space of, now if you are in finite dimensions, say you have a matrix, you can always identify the space of bounded operators from H to H, which are matrices, with the tensor product of H. Actually, if you want to do a good identification, you need to do tensor product of H, which H star, okay? Simply because if you look at this, so if you have an element, say, phi tensor product, so here it's important, ket phi, so on H tensor product bra psi, you can map it to what? This projection operator where you take any other vector v, you do the scalar product with psi, and then you end up multiply this complex number with the vector phi, okay? This is just an identification. If you don't care about really the details, remember, these are matrices. Sorry, forget about the 2. These are matrices, so they have the dimension of H times dimension of H, and this is the same in terms of dimensions. So you may expect that there is a reasonable identification. And in practice is this one. And it's quite natural, okay? It does not depend on any choice of coordinates. Okay, now, this is an identification which is simple to write in terms of starting from a tensor product and go to the operator. So, but you can also invert it, and so we have this notation. So if you start from an operator, let's write this element, which is an element of this Hilbert space, like this double ket notation, okay? This is simply the element in this, so will be a linear combination of elementary tensor products, which represents your operator H. If you want, you can fix bases and represent, I everything in terms of, you can write this in terms of a matrix. I think there are some exercises around here. Yeah, indeed. So this is really identification of scalar of Hilbert spaces. Remember, there is a Hilbert space structure here. And the Hilbert space structure on the set of operators is this. This is also called the Frobenius scalar product, maybe, or the Hilbert-Schmidt scalar product. Okay. So given two operators, you do trace of the A dagger, so the adjoint of A time composed with B, and then you trace this. Okay. This is, if you write everything in terms of coordinates, this is simply a scalar product component-wise of the matrices. Okay. And so you have this identification, and this is also quite relevant, maybe for us, that now if you have an element in a vector on this space, which is H tensor H star, so it's a tensor product. Now remember that on the tensor product space, you can act if you have an operator which maps H into H, so say call it A, and another operator which maps H star into H star, which may be B transpose, right? Because we know that this is a special case of this operator. And you can do the tensor product. What does it mean? It means that if you have an elementary tensor product in this space, you act on the two factors, right? So what happens is quite natural that if you apply this linear operator on the tensor product on some vector which represents H, well, you end up with a vector which represents a natural operator on acting on H, which is simply the composition. You have to be careful that you have on the left with A, then X, and then on the right with B. So first you apply B, then you apply A, X, and then A. Okay. So this looks like algebra, but if you really you can do it in coordinates, for example, if you want to do a good exercise on this stuff. Yeah.
Just one note. I mean, if you ever do C-star algebras and you see A tensor A op, and you ask yourself, what on earth is the op? Right? I mean, you have left and right multiplication.
Yes.
The transpose is actually very delicate for normal algebras. It's not a joke.
No, I'm saying, no.
It's not a joke.
No, here everything is a joke if you want, because...
No, everything is elementary.
Exactly.
But anyway, if any person ever wants to do this dictionary and he sees A tensor A op, this is because he used the transpose and has a long history of complications, right? So,
I agree.
So that there's a little issue with the op.
Surely, because it's still manageable if you work in the space of...
finite-dimensional algebras are not really sensitive to this problem.
Yes, no, I agree with that. In fact, I will jump a bit into the infinite-dimensional case at the very end, but you see, these concepts are, maybe there are two degrees of difficulties. So first you want to understand a bit the algebraic side, and then the topological side, if you move to infinite dimensions. So it's an extra degree of complexity. Yeah.
Could you go back to the last slide?
Yeah.
I want to ask Nathan, the XS1, the formula, should it be phi comma and psi comma psi?
In
the right of the formula.
Sorry, on this one?
Yeah.
Okay, so maybe I missed something. So there is phi against phi prime. So you take the scalar product here. So, but you want the scalar product to be linear, so to be bilinear, but no, looks correct to me. No, phi goes with phi.
Okay. It's just anything in the product. Everywhere here, scalar products are linear in the second variable.
Yes, right. These are linear on the second and anti-linear on the first. Okay, this is what we want usually. Okay, this is a convention in the quantum setting. Maybe this should have been told in the first lecture. Okay, but now let's go to the purification. Now we understand this isometry, maybe not very much, but at least we can say. So the point is, we have a state which is a quantum state which is an operator from H to H. So remember, is a matrix. So what can we say? Well, if we want to find a vector, we can identify rho. Well, already we may have, for example, as a possible choice, you say, well, rho. This is is a linear operator, is a trace class operator, so on. But say we are in finite dimension, so it's a linear operator on H. So thanks to our correspondence, we have this object here, okay, which is instead a vector in H tensor H star. So you say, this may be a pure state Well, the point is that you don't need, since then you need to take the trace of this and paired with this, so you need the projection on this vector. You actually need first to take the square root of rho. Okay, this is the maybe key part. But if you start with this, you realize that there is something wrong. So the point is that really the purification is the vector. So if you have the state rho, the canonical purification is the vector corresponding not to the operator rho, but the square root of rho. How is the square root of the operator defined? If you want, you diagonalize, you take a basis, you diagonalize, and you take square root of the eigenvalues. So you use the spectral theorem, spectral calculus to define this square root. Okay. Now, okay, this is the so-called canonical purification. And K, our auxiliary space, is really the dual of H. Okay. Now, how does it work? Now, you say, as I told you, right, if you define rho, you may represent rho as an ensemble, no, right? You say, remember, you diagonalize rho, let's call it simply I the orthonormal basis of eigenvectors for rho. Yeah? Questions? No? Okay. So you have the sum over I of pi, the eigenvalues, but remember, with multiplicity, they sum to 1. These are actually the probabilities. And you have these eigenspaces that, let's write it this way, the projections on the eigenspaces. And then the square root, as I told you, is defined by you get diagonalized, so we take the square root of the eigenvalues, pi, and then still the projectors. So what is this vector? The correspondence is linear. So here we have these simple projection operators which correspond in H tensor H star to these elementary tensor products. So this is really an explicit expression of the purification in terms if you know the basis, if you know how to diagonalize rho, okay? And now what happens is that you need to take the partial trace. Okay, now remember, if you do the partial trace, you need to take this, which is ket, and pair it with the bra. So you need to essentially do the double summation over I and j. You have square root of pi, square root of pj, which are the numbers, and then this term here, and then the dual. So the dual formally, essentially, you just replace this ket with bra and this bra with ket. Okay, but you will have a double summation over I and j. Now, what happens if you do the partial trace? Do you remember? We need essentially to freeze. So no, maybe we can do it instead of just telling it. So you would have that explicitly. You have this rho, square root of rho. As I told you, this double summation over I and j. You have square root of pi, square root of pj, and then you have I tensor I bra, and then you have what the dual of this, so you have j tensor j, okay. Now, when you do the partial trace, remember, we had in general, what should we do? We should do the summation, taking the partial trace, and we trace out H star, which is the second one, right? So we need essentially to do the summation and essentially contract these two indices, right? So they will contract and will give you something non-trivial only when I equals j. Otherwise, we need actually to do the contraction. So we need to impose that I equals j. But if you impose that I equals j, these are also, they must be equal, right? I must be equal to j. So essentially, you need to just do the summation over I. This I equals j, so you really have pi. And then you are only left with I and I also on this side. But this was our spectral decomposition of rho. Okay, so it's really a matter of going back to the definition of partial trace. Now remember, in general, the partial trace here would have a summation over 4 indices. So maybe already here we have some constraints. So this is why maybe it looks strange, the computation. Now another interesting thing is that what happens if you instead you trace out the system H, you will have something on H star. And you are almost finding, no, here there should not be tensor here, but it just, sorry, this is not, it should be simply a space. So you always end up with an expression which really resembles this one, but you have just the I and j which are inverted the role of bra and kets, because this must be an operator on H star, from H star into H star. So, but this will be the transpose operator of rho. So not only you have a purification that gives you, on the first factor, gives you back rho, but the canonical purification on the other factor gives you rho transpose, which is quite useful. So you built somehow, up to this transpose, you built the 2 copies that we wanted. So we have a pure state, and if we trace out one system, we find rho. If we trace out the other system, gives you rho transpose. Okay, this is a good thing. But this goes back really to the early days of quantum mechanics. Actually, you can, I don't know why you have this. Well, let's keep it. Okay, you can also play a lot with this thing and find other spaces if you need to enlarge a bit the system, but forget about that. So now the point is we have this good way to build our starting point, which is the canonical purification. And in some sense, the canonical purification should be the coupling in our setting where we don't move because we have already rho on one side and rho on the other side. And now we can define a new notion of couplings. What we recognize essentially is that we only need to massage a bit the definition of Gauss, Cagliotti, and Paul, and say instead of requiring to have rho and sigma, we look for a state. So we define a new class of couplings. These are not in general the same as the Gauss and Paul, Cagliotti couplings, because we look for states on the tensor product of H with not a copy of H, but H star. Okay. Now this may look a bit strange at the beginning, but I show you that this is a good definition which is in correspondence with the plans. Okay. So what is our requirement for a coupling? When if you trace out H, so the first factor, we want to find rho, but actually we cannot find rho because it lives in the wrong space. So you will find rho transpose. Okay. And if you trace out the second system, you find sigma, which is a good state on H. Okay, so this is a new definition, which is, if you want, inspired by the fact that if you just do the canonical purification, you find the rho and rho transpose. So in some sense, the canonical purification, which corresponds to the identity coupling because we haven't moved the rho, and we have rho on one side and rho on the other side, is a reasonable coupling. It's a coupling between rho and rho. But we can find other simple couplings. For example, you take a product. Now you have to be careful because on the second factor we have H star dual. But this is a coupling which corresponds intuitively to the fact that we have two copies, sorry, not two copies, one copy on sigma and one copy of rho, which are independent. Right? In the classical optimal transport, if the transport plan is a product, this means that the two random variables are completely independent. You're not actually coupling, you're just uncoupled. Okay? So these are two extreme. But there are some remarks. We have a trouble. So as in the Gauss, Paul, Cagliotti definition, you remember there was this exercise. If one state is pure, you have not much choice for couplings. Essentially, in their case, but also in our case, if you want to move a pure state, so I write it this way, but you have not much choice for the coupling. The coupling is only the product coupling. Okay. This is the point. And this says that you're not doing a good transport if you want really to compare pure states. Okay? But this is a good transport if you have mixed states. There might be good couplings in this case. And, well, there is a correspondence. Okay, this looks a bit not symmetric because you have on the one side the transpose and the other side you don't have the transpose, but you can change, you can swap and take a transpose and you will have a correspondence between couplings from rho to sigma and couplings for sigma to rho. And then you may say, okay, but then since it's just a matter of taking a transpose on one factor, I also have a correspondence with the other couplings, right? Well, there is this point that you can act with the transpose only on one of the two factors. But this is what is called the partial transpose operation. Okay, and the partial transpose operation, fortunately or unfortunately, I don't know the point of view, because is not a channel. Okay, so the transpose is not a channel. Let me give you this remark. So so the couplings, let's say the C of rho and sigma are defined in this way, right? They are subset of the states of H tensor H star, while the couplings, if you want by Gauss, Paul, and Cagliotti, between rho and sigma, are a subset of the states of H tensor H. Okay, so these are linear operators on this space, into itself, and these are linear operators from H tensor H into itself. So we can make a correspondence, yes, because if you have a linear operator, like an elementary linear operator, well, let's do it this way, maybe it's more natural, sorry. So if you have an elementary tensor product between this, an operator on H and an operator on H, you can map it by taking the transpose only on one factor. Okay, so at least in terms of linear operators, you have a correspondence. You say, well, sorry, star. Okay, you have a correspondence, and this you can extend by linearity, right? Any linear combination of operators of this type will give you a linear operator, the same combination there. But now, what is the point is that this map is, if you want, this map is identity because you don't act on the first factor tensor. Let's call it phi t, where phi t is the transpose. So phi t takes A and gives you A transpose. Okay, you would like this map to be a channel, a quantum channel. And in fact, if you have a state, and you transpose the state, well, from a single point of view of a single state, you will see if you have a matrix, for example, if you have a matrix, now you take coordinates, you take the transpose of the matrix, it will still be positive semi-definite, and the trace will be 1. So you say, well, this may be a channel, but it is well known that this is not a channel. So what is missing? Well, it's exactly the complete positivity. So if you do the identity tensor phi transpose, exactly this map here does not map the states into states in general. And the simplest example is, again, the Bell state. So can I erase here? Or example or exercise, maybe we can do it together, so it's simple. So consider, this is well known, it's not something that we discovered, but it's an important thing to know. So if you have the Bell state, so let's take, let's call it phi, right? Our Bell state on the system of 2 qubits, okay, just to be, right? So this is a vector in C2 tensor 2. And so if you do rho, the pure state associated to it, okay, this will be a state on the system of 2 qubits, no? C2 tensor. Okay, now what happens if we act with this partial transpose? So we just transpose the second, okay? Now maybe the simplest thing is to say, okay, let's look at the matrix. What is the matrix which represents this? Well, you have 1/2. So what will be this? We can do also if you want, the computation, but you see, you just write phi in this way. The dual will be a similar expression, but here you reverse the cats into bras. Okay, so let's do it. So you have 0. Sorry, this is something. So these are reversed, and these instead are the original. And then, of course, you have a factor 1/2. Okay. So but let's focus here. We have this projection here, which is simply the projection on the first element of the basis. Remember, we look at these as binary strings, so this will be in order 0, 0, 0, 1, 1, 0, 1, 1. Okay. So this corresponds to the first, the second, the third, and fourth component. And also here, 0, 0, 0, 1. Okay. Just to tell you which order we write the basis. Okay, so the first one will be this, which corresponds to a 1 here. Then you will find 0, 0, and get 1, 1, which is row 0 and so first row, sorry, and the fourth column. Then you have 1, 1, 0, 0, so you get this one, and then the final one will be 1, 1, 1, 1. So you get, and all the other entries will be 0. Okay, you have a lot of zeros. So it's a block matrix of this kind. Okay. Now, what happens if we apply the partial transpose? So on each of these elementary states, what are you doing when you apply the partial transpose? You leave the first the first pair fixed, because you're acting with the identity on this system, and you transpose, so you just swap these two. 0, 0 will stay 0, 0. Now what happens instead to 1, 1? Well, we stay 1, 1, but the point is that if you partially transpose 1, 1, 0, 0, you need to keep this fixed and you swap these two, so you will have 0, 1. So you have that now this entry here, yes, which is 1, 1, 0, 0, will move here, okay? And this one will move here similarly, okay? So this is rho. Instead, rho partially transposed, you see this transposition here on this. Actually, you are acting on each of these blocks, you are applying the transpose, okay? This is what happens. So we move to a different matrix. And now this is rho partially transposed. You see this is a matrix, this is a permutation matrix, which simply exchanges the second and the third components, and this has determinant -1, okay? So this is still symmetric, of course, but the point is that it is not anymore a positive semi-definite, okay? The trace is still 1, but it's not a positive semi-definite, okay? So this correspondence, so there exists a general correspondence between linear operators, but does not map states into states. So except trivial situations, we have that this is a different notion of couplings, okay? But this is a different notion of couplings, which, questions on this? Well, which is in correspondence with transport plans, okay? So if you're looking for a coupling which has a meaning in terms of channels, in terms of plans, this is a good note, okay? Because in general, given a transport plan phi, remember transport, oops, okay, starting with this. No. Let's see, otherwise I'll okay. So given remember, we started from transport plans, which are channels. So if you have a channel which maps rho into sigma, so you can induce a coupling. How can you induce the coupling starting from the channel? Well, we already built these two copies of rho, no, this purification, and we have one system which is H, and the other one which is H star. So what we do, we act with phi, which is our plan, on the first copy, and we don't act on the second one. So what we do, we apply phi tensor the identity which acts on the linear operator on H star, because we're on the copy of H star, we leave that untouched, and this gives you a coupling. Okay, simple to check. So at least you can say, given a plan, you find a coupling in this sense. Well, and actually this is positive because you see you are doing phi tensor the identity, so the fact that this will be still positive is because of complete positivity. And you can check, okay, this is maybe not so easy. So the point is that since you're acting only on the first factor, when you do the partial traces, the partial trace over H star will enter the action of phi, okay? We need maybe some more properties on the partial traces here. But then really, at least intuitively, we have these two copies, so we send the first copy into sigma, and the other one will stay rho transpose, okay? Maybe the less trivial part is that actually all these couplings, the one we defined, are induced by some quantum transport plan. So we can really find, given a coupling in this sense, not in the Gauss sense, you can find a channel. And how do you build a channel? Well, to build a channel, you need to build some Krauss operators, okay? So and the idea is essentially to look, maybe this is also called, it has a name. Also this idea is somehow in the theory of quantum channels is also known, I would say, but we just work it out again. So in case, so the point is this one: you take your coupling. Again, you use the spectral theorem. So the spectral theorem will give you this decomposition. Coupling is a state, so you can always diagonalize. The point is now it's a state over H tensor H star. So you will find these eigenvectors which correspond to linear operators. Okay. And also you have the weights, which are the probabilities, which sum to 1. So the point is that starting from these operators AI, you build the Krauss operators. You remember, quantum channels can be expressed, is a useful way to think in terms of quantum channels, at least to operate with them, in terms of Krauss operators. Now, the point that BI is not really AI, because what you need essentially to make sure that you will send rho into sigma, right? This is our condition. So the actual BIs, okay, maybe I will not enter the detail, are defined, you see, in terms of AI. You need to invert rho, which is, if you want, is a sort of, you take 1/2 to the power minus 1/2 rho. If you want, it's a sort of non-commutative way of, classically what we did, we started with pi of xy, and we built our pi of y given x simply by taking pi of xy and divided by rho. So somehow this is a non-commutative analog of this operation. Okay, you start with pi and you want to build the kernel. Okay, you build the Kraus. Okay, and now okay, there is something to check, but maybe we can really skip on this. Okay, so we have this notion of channels which corresponds to couplings. So plans correspond to couplings. So now we can really follow again what was done previously, right? We follow closely the same approach by Gauss, but now we can really transport, say, we have a reasonable way to say that we are transporting rho into sigma, okay? So given an observable, a cost observable C, which may be a sum of squares, and actually this is what we're going to fix, but maybe other things given the application that one has in mind, you do the cost, the transport cost. It's maybe sometimes I write it also as C of pi, right? Which is simply the trace of C pi. Okay, the observable. We're always in finite dimensions, so no problem to define this quantity here.
So abstractly, the cost is in the tensor product of.
Yes. Okay. This is maybe it must be specified because with respect to Cagliotti and Gauss, the point is that now the cost is an observable, so it's a linear self-adjoint operator on H tensor H star. Yes, you're right. So maybe it's not completely obvious how you should find. So if you have a reasonable cost on H tensor H, you should maybe act with a partial transpose on C. So for example,
that is exactly the, if you do it in normal algebras, you'd say the cost is an A tensor A op.
Oh, that's good.
Right? I mean, that makes sense. It's just very counterintuitive what they do in other parts of quantum info. But I mean,
right. I mean,
but from an operator algebra standpoint, A tensor I op is very justified.
Yeah. Okay. Good. Good to know. This is something I read.
It makes things harder.
Yeah. The point. Yeah, but you see, this operation of taking the partial transpose. So, for example, I have a reasonable cost, and then I do the partial transpose. I'm acting with this operation, which is a bit shady, I would say. If you start, you say it's naturally in this space, it's okay. But then, for example, one choice that we studied very much is the sum of squares. So now, if you do the sum of squares, what do I mean? You fix, say, these n self-adjoint operators. And you do this cost, which is a sort of Euclidean cost. You say sum over the n, I between 1 and n. You do Ri, which acts on H, tensor the identity on H star, minus the identity on H, but then tensor the Ri transpose. Okay, this is what you need to do, because otherwise you are in the wrong space. And this difference, this discrepancy, if you want, is between the two. You want to measure whether Ri is similar to Ri transpose on the transpose on the H star. Well, you square it and you do the sum of squares. Okay, this is one thing that you can do, but you can. There's been some attempt to do, for example, the p power cost thing by some group in Budapest by Daniel Virostek. But I mean, it's natural, but there may be other natural costs. Okay, this is something quite open, I would say. Surely, if you are looking for a coupling, which is also a channel, you must, I think, go to this setting. So now the transport. Yeah.
Just one question. Despite the fact that if you take a coupling here or a channel, then you do transpose, you don't get something like a coupling for the setting of Gauss and collaborator. But if you take this cost and you try to move back to H times X, at least aside the problem with the coupling, the cost is this kind of similar to the one they use. If you
yes, I mean, algebraically you're just taking a transpose. Right. No, some properties can change. Some spectral properties can change. No. So given this, but you see, the spectrum. If you act with a partial transpose, the spectral can change. Right. This is already one example. Right. No. You go. Yes.
I'm just wondering, so as far as I understand, like the C is trying to imitate, like in the classical case, we have like a square of, or like sum of x minus y. But
Yeah.
like, or like we can say that x times identity on the other space minus identity
Yes.
of like 1 of x and times y. Why don't we sum like in terms of like sum I and j are I times identity minus
RJ.
identity times rj?
No, because what you're saying, I have this. Say I have this n observables on state. The state is rho. Maybe these are the observables I can measure, like some positions, some moment or stuff. I want to say, okay, if the system is in state rho, I will have these observables. If it is in state sigma, I will have these observables. But I want to compare each with each. I'm not want to compare the position. Of the particle, of the first particle with the momentum of the second one. This is something I don't want to.
Classically, you don't do like x1 minus y.
Yeah, classically, you should think of a vector of R1, Rn like the coordinates.
Or you mean like when we apply these ones, it would kind of imitate that like we, the end of the application is already like x minus y.
I mean, classically, you should think of Ri tensor identity as functions of x, and identity tensor R as functions of y.
Right.
So,
and you're saying I compare this function
this is exactly
of x
what I was
with
thinking, but like then you would probably think that okay, so the function of y should be independent of the function of x, and here we have the same index, like Ri and Ri.
because the ith coordinates is on both sides.
Okay, but we can go back on this. But it's really that you think of R1, Rn, if you want, as n random variables. You want to compare what happens if I change the law on the underlying space. Okay, you may think of this, but okay, we can go.
Commutative spaces don't see the op. Commutative spaces don't see the op.
If they commute, yes.
There, right? I mean,
yes, if they all commute, if everything is commutative, yes, the situation trivializes in some sense. No, now going forward with the definition, the cost is the same as Cagliotti, but now I just say Cagliotti because it's the last one. And then the distance, okay, is again you minimize over the couplings the cost, and this should be a sort of squared Wasserstein distance. If you know a bit of the classical setting, this should not be a distance by like the square of a distance. So the conjecture is that the square root of this, so this quantity that we simply write with d without the square should be a distance, but actually it's not in general. Okay, there are some issues. I'll show you some properties that we have. Okay.
Sorry, Dario, I don't understand. So classically, sigma of x would be a mass density at x.
Yeah.
But in the quantum case, sigma of r
So you're
is the expectation value of the operator Ri. So in this trace of C and pi, you will have expectation values.
I'll show you now a different expression of this, because this looks very abstract. You say, well, what are we doing? The point is, you can work out some explicit examples. For example, if the coupling is a tensor product, this cost will reduce to this quantity here. Okay, but you say the tensor product, so you're doing essentially, they become independent, sigma and rho, so you have just the trace of sigma Ri, so you have the second moments, if you want, minus twice the trace of the first moment, sigma Ri, okay?
Just make sure I understand. So in general, even if it's not a tensor product like this, the first two terms in the sum will remain so.
I show you I have a general expression now. If it's pure, you can also work out if one of the two is pure, the only coupling is this one. So remember, if it's pure, it's quite trivial. The situation trivializes. So this is the only coupling if sigma is pure. So this is our D. So if you want to work in the case of one state is pure, this is the expression. So maybe you want to compare a pure state with something which is non-pure. So maybe this is a situation. But now, in general, okay, you can work out an expression. Maybe we don't have enough time to do the details, but you develop the squares. You understand that your coupling is maybe explicitly given in terms of a plan, phi. So you work out a bit the algebra, and you end up, let's see if I have the expression. Oh, okay, here, this is the other expression. So given a coupling which is induced, so I still write C of pi, but now you need to think of this coupling pi induced by a plan phi. So you have your plan. And so the cost, remember, is the square, the sum of squares. So you have contributions. These terms, you see, they depend. These are sort of moments. And maybe I have another expression as well. No, okay, okay, but look at the first line. I think is more explicit, right? So you have the sum of the second moments, Ri and Ri squared, which is fixed. So this, you cannot do anything here. There's no phi. So this is second moments, as you would have in the classical setting of Wasserstein 2. If you do the square distance, you can develop the square. This will not change. So phi only enters here. So you have the sum over all your observables Ri of this trace of Ri square root of rho. And then you have phi dagger of Ri. What is phi dagger? Is the adjoint of phi. So when it's not the map which maps states into states, but the one that maps the observables into observables. Okay. So, but it's you can think it's the dual version of your map phi. So something which moves, if you want, the observable Ri from the system rho from the system sigma to the system rho, if you want, and then another square root of. So this is really the non-commutative analog here of what you would find in the classical case. You would find something like x scalar y d pi. Okay. If you develop the square, this is like the quantity. This is a covariance, if you want to. And this, since there's a sign minus, should be maximized. Okay. If you want a more explicit quantity, say explicit up to some point. Okay, it's not really. Maybe an answer, okay. But now, if you want, you have an explicit expression, which is something that you work with because you connect a lot with expressions of this kind, which appear in other areas of quantum information theory. If you want, you have all these Lib inequalities of monotonicity type and so on. So essentially, you have two parts which are not relevant. You cannot maximize on this, and then you can minimize. This one with a sign minus, so you are trying to maximize this sum over I of these expressions. If you want something more concrete in terms not of these purifications and stuff, but in terms of channels, okay? Now, you can play also a lot with this. For example, why do we have square root here and square root there? Perhaps you can put the square root together and try to maximize the sum of the trace of Ri, phi dagger Ri, and then rho, okay? This attempt has been done by Rocco Duvenage, and gives you something which has, I may say, it has similar and maybe even better properties in some sense. So you can still play a lot with these definitions. Now, starting from our definition, we have...
Sorry to interrupt, but I mean, that if this is the KMS in our product, which Colin and Maas...
Yes, yes. You can
there's
also...
a lot of connection, and they also tried these different powers.
Exactly, exactly. I mean, this expression, I like it appears because it's more related to these other approaches, but still we are not able to relate this approach to Carlen and Maas approach, okay? So there is this, yeah, we're almost there, I think, but there is something. For example, okay, let me give you some properties of this distance or this cost square. So now, if you take the trivial case, for example, the distance between a state and itself, you would like not to move, just to stay there, and this should give you the optimal transport, possibly. Because the cost, at least classically, you say, if I don't move, the cost is 0, okay? Now, if sigma equals rho, and you take as a channel the identity, so you don't act, the coupling is really our friend, the purification, and the expression is precisely this. You can recover it, okay? Now, what happens in general, let me show you. Well, no, I don't have an example here. The point is that if these Ri's do not commute, okay, we have it here, okay, I need to go back to the very end. So this is just one case of a cost. You may say, is this the optimal thing? Perhaps there's a way to do a coupling, move something around and make something smaller in terms of cost. Well, actually, in general, we can prove, we actually rely on these inequalities by Lib and all the Lib's concavity inequality, monotonicity inequalities. Well, you can prove in general that the cost, the squared Wasserstein distance between rho and sigma is always larger than 1/2 the cost of the purification of rho plus 1/2 the cost of the purification of sigma. Say, okay, this is a general inequality. What does it say? Well, it says, for example, if you take rho equals sigma, this tells you that the cost is always at least the cost of the purification, which is the cost of doing nothing. So in general, we can prove that the identity channel is an optimal plan, okay? Which is something that we don't have in the other approach, the one by goals, okay? So we have at least the fact that if you don't move, you are optimal, okay? In this case, okay. Here we're really using that the cost is the square of the structure, okay? Because of course the examples that Augusto was mentioning last time, if you have a repulsive cost, of course you want to move, okay? You want to transport. Okay, we also connect. Now, if you now realize that this is the cost, you can go back to this expression. And you realize that this is something already known. This quantity is the so-called Wigner-Yanase square norm, okay, which is a quantity which is non-zero in general, okay. So what happens in that is that the not moving is optimal, but sometimes you also pay a price by staying there, okay. This is due to the fact that this Ri may not commute, okay.
Well, this is not a distance metric then.
Sorry?
It doesn't satisfy the distance as a metric. It's not a metric. The self distance should be zero, right?
Should be zero, right? In fact, so this shows that this is not a metric, okay, in general. So even call it a metric is a stretch. So in fact, yeah.
Are there any costs for in general? Are there any other expressions involving RIs in general without assuming commutativity, which would give you zero for the identity coupling?
Yeah, if you take the Duvenage approach, so you put this rho here, so you change this KMS.
Don't change the cost. You're only allowed to change the cost, not the setup.
If you just change the cost, okay, this is not really changing the cost because now if you change the cost, well, if you take zero, okay, so if you take. No, okay, I would say a non-trivial thing which I appreciate by Duvenage's approach is that if you push a rho here, you still have something which in a commutative case is okay, but the self-distance becomes zero, if I remember correctly, so which is interesting. So perhaps this is a better approach if you want to have the self-distance which is zero. Another thing that we try to conjecture is that perhaps it's like when you do this entropic regularization, you know that if you do optimal transport, the entropic regularization, the self-cost will not be zero in general if you add a constraint on the entropy. And so what people defined are the divergences. So they take the cost, you subtract 1/2. We know already that this subtraction gives you something positive, so maybe the square root of this is a distance. Okay, maybe this is a good conjecture. So far what we're able to prove is that because remember, you can always take the cost to be identically zero, so of course this trivializes everything. But if the dimension of the space is finite and the observables that you choose generate as an algebra all the operators, okay, then if rho and sigma are also invertible, this is also important. If this divergence is zero, then the costs are the same. So it's a good way to distinguish between two states, at least in this, when these are invertible operators, which means they're very far from being pure states, okay? This is a good distance from states which have full support, if you want. Well, not saying about the triangle inequality. Triangle inequality is a different story. Okay, now let me skip on this part. So yeah.
But how can we take like rho and sigma invertible if we want them to be like density matrices, so their trace have to be equal to 1, so they're at least compact operators, so they're
find the dimension.
Okay.
In fact, there is a nice application. For example, they were studying the isometries on the single qubit. Don't think about the infinite dimension space. In the infinite dimensions, you require the support to be full. So you have full support. But you still have, in infinite dimensions, you will like to have something which is unbounded here, unbounded operators, so it becomes more tricky, this part. We still haven't worked out all the details. Yeah,
Sorry, do you need this to generate the algebra as a Lie algebra or as an algebra?
No, really algebraic as an algebra. Say just.
The conjecture would be for a Lie algebra, right?
Well, no. Why? Because classically you would say I have x and y, so I have the coordinates. The algebra would be the polynomials, so you say the polynomials are dense. This is
then it's
dense in the sense of an algebra, not
sub-Laplacian, and the sub-Laplacian is ergodic.
Yeah, okay, maybe we can think about this other approach. Okay, for us, the condition is to algebraically generate for the moment. Okay, so this gives you something about the triviality and non-triviality. If you want to use this distance to measure whether actually two states are equal, you can, at least in that finite dimensional setting and generating as an algebra and so on, you have some non-triviality. Now, the point is, the next point is a triangle inequality. Can we say that we have a triangle inequality? Well, it turns out that we have a sort of modified triangle inequality, which tells you this. If you have the distance, so you do the square root of this d squared, which you expect to be a distance, except that the distance from rho to rho is non-zero. So it happens that from rho to sigma, you can always bound from above in terms of distance from rho to tau, a different state. And then you have the cost from tau to tau, which is square root of the cost, which is maybe positive. And then distance from tau to sigma, okay? So somehow it's like if you end up in tau, but you need to pay a small price to stay there and then move from tau to sigma. Now, in general, we don't know, this is simply something we still don't know whether this can be removed, okay? So maybe the inequality is also true without this distance from tau to tau. But again, this is not interesting because d is not a distance in the sense that distance from tau to tau may be positive. So the point is there a triangle inequality for the W2, the Wasserstein divergence? So in the group in Budapest, Daniel and Bunz in particular, they proved that if at least one of these states between rho, sigma, and tau is pure, which you say trivializes a lot, but still it's non-trivial, I would say the result, the actual inequality for the W2 holds, okay? And similar inequalities, I would say, for the other case without couplings are quite open, I would say. Are not known, okay? Maybe we don't have time. Okay, maybe just a couple of words about the Gaussian, a couple of words about the proof here. The point is, why we don't know how to do this for the Gauss, Monod, Paul Cagliotti case. The point is here we have couplings that are correspondence with channels, and you can do a composition of channels. So if you do a composition of channels, you have a channel. Okay, you have a quantum channel, a completely positive, trace preserving, and so on. So this is quite natural. And then, so if you want to move from sigma to rho, you would just take an optimal channel from rho to tau, and then a channel from tau to sigma, and then do the composition. This gives you a channel from rho to sigma, okay? Now, you only need then to work out all the math, and it turns out that there is this extra term which appears, okay? So far, we're not able to remove it. But at least the idea is very simple in terms of channel, while in terms of couplings, you would need to do, classically, when you prove this triangle inequality for the classical Wasserstein distance, you do a disintegration, and you glue together the disintegration. So essentially, you're moving, maybe you don't say it in terms of probabilistically, but you end up moving from couplings to the kernels, to the Markov kernels. Because you can make a composition of Markov kernels, but not of these couplings, okay?
But here it's a relative tensor product, right?
Sorry?
Here it would correspond to a relative tensor product.
Yes.
It would correspond to that, yes. Okay. Yeah, but you don't have it again. No, but again, maybe interesting to know if a similar inequality holds for the. I'm not saying it's false. I'm not sure. Okay.
That's a quick question.
Yeah.
So in the classical, two Wasserstein case, you get a lot of structure showing up, like cyclic monotonicity, gradients of convex functions. Is there nice structure that emerges with this squared distance?
Okay, let's put it this way. You would like first to understand duality, and now a lot of effort has been done in this case, essentially by Augusto and Lorenzo, but and all the group. But the cyclical monotonicity, I'm a bit skeptical on that. Okay, also Gauss, they proved something about the case where transporting a classical state into a quantum state. So in this sort of semi-classical transport, you can do something because at least one of the two is classical. But in general, no, I don't know. This is a very open. I guess already understanding, say, the duality in a good way from this point of view with channels maybe can give some intuition about properties that are not have not been explored so far. So this is a.
Just a small comment. I mean, the origin of cyclic monotonicity classically is the fact that the bistochastic matrices, the extreme points, are permutations.
So you say you are very skeptical on this, yeah. No, I agree.
One of the reasons why.
Yeah, but still maybe some partial, well, I don't know, something can be explored. Yeah, the dual formulation for this is, but also other costs. So there's been some progress, as I told you, on different costs, if you don't like the quadratic cost. But, yeah.
Sorry, can I ask as well? Very often we talk about channels, obviously for general channel there's no guarantee that the input and the output space are isomorphic. How far does this framework extend when you don't have that guarantee that you've got
You won't say I want to transport, yeah, you say I have one state which is in system H, the other which is in system K. Yeah, no, you can work it out. At least the point in that case, you just simply say, yeah, take the purification of one of the two, I act with this channel, and I will end up in the product of the correct spaces, up to a dual in one factor. The point is to end up with reasonable notions of cost at this point. Okay, you should fix some observable. If you want to do the sum of squares, you can do it. I don't know other reasonable options, but this is something. Yeah, I think the math is really the same. So maybe in the book I told you in those lecture notes I try to do generalization on two different states. Yeah, so maybe just a couple of minutes. So I will not enter into the details here. But why we like quadratic cost typically? Quadratic cost is good for many reasons, sort of Riemannian-like structures, autocalculus and stuff. But also you have explicit examples that you can work out, because if you have the classical Wasserstein distance between two classical Gaussian densities, distributions, you can explicitly find a formula for that. So the question is, can we do a similar thing? Well, the point is you need to define what are Gaussian states, and the reasonable setting is to work in infinite dimensions. Okay, you start with you need to work out essentially the harmonic oscillator setting. Okay, so you need to find position Q and momentum Q observables, which will be in general unbounded operators, which satisfy canonical commutation relations. And this gives you, actually the Hilbert space, you fix L2 of R, right? And you have these two operators, which gives you a realization of these relations. And then you end up with essentially all the maybe operators that you have met, or maybe you have not, if you have not studied a course in quantum mechanics, right? But the key point is that you can describe what are Gaussian states. Informally, Gaussian states are those of the form exponential of a polynomial, a quadratic polynomial in the variables Q and P, if you want to be very, very informal. And you can also characterize quantum states. So there's a lot of, there's a lot of algebra and a lot of properties that are very well known for Gaussian states. Okay, more generally, you have an expression of this kind. Okay, a quantum state is a polynomial of second degree, is a Gaussian type if it's an exponential of a polynomial second degree in these quadratures that can be or even more than one position and momentum observables. Okay, so if you stick with me for a second. So if you have these Gaussian states, you say, okay, now the quadratic cost is quite natural because I have the analog for the classical case, and I try to do the similar thing. You have to be a bit more careful because if you want to define this cost, this will be an unbounded operator. So you have to be careful with domains and so on where this is defined and how is this trace of C pi defined. Okay, but you define as you would do in the classical case. Usually classical optimal transport, if you have an unbounded cost like the squared or the distance to the power p, you need to restrict to probabilities which have finite p moments. But this is a similar situation. Okay, but once you believe that everything can be done, you have a nice result, which tells you that if you have two Gaussian states and you have a quadratic cost, as I told you before, of the quadratures, well, the distance will be actually attained by some coupling, which will be a Gaussian in this, so a Gaussian state in this system. So the coupling will be a Gaussian, and also corresponds to a Gaussian quantum channel. Okay, so something which maps the Gaussian states into Gaussian states. So these are objects which are already well known and understood. So in some sense, we have at least this good family of examples in infinite dimensions that we can work out, and actually this may lead, for example, to numerical schemes, because we have formulas, for example, in the case of so-called thermal states, so isotropic Gaussians, okay, exponential of minus beta and then the number operator, okay. And we have an explicit formula for this, but if you want to know more about Gaussians, I guess we should ask Fanch, because he's been working on this and actually much more also in the entropic regularization of these things, because also for entropic regularized optimal transport, if you have a quadratic cost, you may find out formulas if you want for Gaussians in the classical case. So this is a good setting where you can understand the things and maybe then go a little beyond in the infinite dimensional case for some specific examples. Okay, so I'll stop here for the channel part. So tomorrow we're going to discuss a completely different approach based more on duality, so closer to the Kohn and Lot approach. So if you want more on this, I think you can find the chapter here on in the book I already told you about. Okay, thanks.